Hi again. Welcome back to Fall CS 170. We're on week 4. We're doing the lecture for chapter 9 right now. Before I get into that, I just want to remind people if you want to look up the contacts for the TAs or myself, just look in the recitation locations. You'll see your sections, you'll see the email, and you'll see the person assigned for each section with myself assigned to cover all of these sections. So feel free, reach out to us if you have any questions. Let us know if there's anything that we can do to clarify any topics that we're covering, and we'll get back to you as soon as we can. Okay, let me close this. So here we are. We're on chapter 9. Um, I think one thing, I have some notes down here at the bottom, is to remind people we were doing the web searches. So you remember that there was like and, ors, nots. Just remember that you can't use the not, you have to use the minus sign when you're actually doing the search. So if people don't remember this, let me go back to my browser here. And when I was doing it, remember I was doing it with images. So we did tigers, not baseball, let's say. And let's go to the images. Okay, so this comes through pretty clear on how the search will show only the tigers and not the baseball tigers, right? But you can't do not baseball, right? So if I do a not here, okay, so that doesn't work. And back to here, right? So I know some of you, when you did your extra credit, you were kind of showing like the all here or news maybe. Uh, I think when we're doing stuff for what we're doing here in the class, it's good to use the images to make it pretty clear on what's in and what's out. So you can match up to your Venn diagram pretty cleanly. So anyway, that was just like a little note that kind of came up. All right, so chapter 9 covers a couple of different things, really kind of coming back to the computer. We were talking about stuff with HTML. So that topic is kind of closed out right now. So one aspect, it's sort of related to abstraction, which we talked about in some of the earlier lectures. This idea of layered software development and software layers. So it's a simple concept. I'll show that to you a little bit later. This fetch execute cycle, and then all of these pieces here that fit into that is a notable topic, and this will be something that's important for you to know for the exam. Okay, so there's this idea of this fetch execute cycle, and then within that, how do these pieces fit together into that? So there's the memory, there's the CPU, which has a control unit, ALU, which is an arithmetic logic unit. You have your input output. There's a program counter. There's like these branching and jump instructions, instruction interpretation, computer clock, and clock tick. Okay, so we'll be kind of going through that for this lecture. All right, so we have like a couple of different basic things. Right, you have a processor that follows the program's instructions. You have the operating system, basically handles all the different things that your computer does. So if you want to store stuff to your disk, or write something out, let's say to the printer, to the computer screen, something like that, operating system handles things like that. Software is various programs that you run. Um, there's these instructions, this fetch execute cycle, which I'm going to come into in a second. Memory that stores the data. There's different types of memory, which I'll elaborate more on. And then the hardware, which would be the physical parts of the computer, like the the memory, or the RAM, I guess, on the computer, the CPU, and stuff like that. All right, so here's like a little picture. There's a link to it here, and then just kind of cover it quickly. So here's the input. Right, this would be stuff coming in. It could be coming in off the network. It could be coming in like from your keyboard. You're typing stuff in, and then this is like storage that is pretty accessible, but not necessarily in the central part here, right? So the stuff that's here is the closest. That's the things that the computer or the CPU is using. So it's the most close, so it's the fastest memory access. It's like the working memory for the CPU. And this type of memory or data storage is pretty close. It's still in the computer somewhere. Generally, it could be like you could stick a memory stick or something like that, add it onto your computer. But in computer terms, it's relatively far away, right, relative to the CPU, right? And then there's different things that will come out based on the calculations that you've done here. What happens here, we're going to drill into in a second. Okay, so this describes it some more. Okay, so what I was saying before, random access memory, right? This is your RAM. So with the computers on, you can store whatever you want on there. When you turn off the computer or turn off the power here, the memory, essentially, whatever was in memory is gone. Okay, so it's volatile memory. If you use it while the power's on, that's great. Once you're done, that's it. You have a hard drive. This is something that is fairly far away from the CPU. So the I/O or the data that you go from here to here is relatively long. It takes a long time compared to this memory here. So I guess you can call this like remote storage or so. Could be your disk drive, could be your memory stick. If you're using CDs, I guess you can read stuff from there. And this is more stable. So when there's no power, you still keep whatever is in memory there. Okay, that's still available to you. This is your I/O here, right? So your keyboard, your mouse. You have stuff coming out that can go to your printer, it can go to your screen. And then here's your CPU over here. Okay, and then this is your arithmetic logic unit. Okay, and these kind of work hand in hand here. Okay, so here's some processing. So here's the CPU. Within the CPU, right, within the box, you have a control unit, and this is your ALU, arithmetic logic unit. These are your registers. Registers is really memory. Okay, it's working memory for the CPU. Very fast and very close to the work that has to get done. And the program counter, that just keeps track of where you're at. Okay, so this is just trying to show like some simple addition going on. So essentially, you have two numbers, let's say A plus B. You're going to add the two of them together. Okay, so this move operation basically takes whatever is the value of A and puts it into this EAX. Okay, so like I said, register is basically your working memory. So very fast, it works with it. So you load the value of A into EAX, this register. You take the value of B and load this into this EBX register. Okay, this is just something you can maybe draw a picture and just show this happening. Okay, and then it does this thing called add. right? And kind of an unusual thing that maybe for non-computer science people, they have to get used to. So normally you would take like these two values and then you have something like a third place to put C. But the way it happens within the computer, there's something that they would call it as an accumulator, right? So you would take whatever is in this one, EAX, and whatever's in EBX, add the two together, take the results of that, and store it into EAX. Okay, so you're not going to have like a third register or a third variable to hold this. It actually kind of recycles um, the first register or first variable to store the value. Okay, now, but you actually want to take this variable and send it out to the rest of the computer. Um, so now you have to take this value, EAX, and move it to C, and then it goes back out, and then there could be other things that follow this, whatever. So that's what happens, right? So you have these values that came in from the outside, and then all of this stuff is basically just taking the input, using its own local work area, do some calculation, and then kick it back out by assigning this value, the results, into this C over here. Okay? So the way you can look at this fetch, decode, and execute cycle, it's almost like if I have to run a computer program, so first I have to get the instruction. I have to know what I'm trying to do. And then usually when I'm doing something, I'm acting on it, right? So maybe I'm getting some information from somewhere and I'm going to add to it or whatever, right? So I have to basically almost be like I'm getting the recipe, right? And I'm getting all of the ingredients uh, to execute on that recipe, right? So that's what this fetch is all about, right? So a recipe, you know that there's going to be different steps that you're going to follow, okay? But once you have the recipe and the uh, ingredients, um, you're basically going to have to decode this, right? So translate these instructions. And just like what we showed up here, you have these registers that you're working with. That's what you're going to be doing here, okay? Um, so once you figure out what to do, um, then you're going to execute on it, which is this blue part down here at the bottom, okay? Um, and you know, as we showed up here, you did execution, then out comes this C over here. Okay, so generally, and you kind of see at the bottom here in my notes, you know, it's this circle action here. Starting from here, you get your instructions. Once you figure out what you're going to be doing it with this decode here, and remember you have to get the ingredients, right, to execute on this recipe, then you do the execution here. So that's what they call this fetch, decode, and execute cycle, okay? So this kind of lists it more explicitly, right? So you, as I said, you get the instructions, you fetch the instructions. Um, you have to understand what those instructions are telling you to do. You have to get the data, right? And how you're going to action that data. Then you're going to have to execute on that instruction, and then you're going to have to return the result and store it into memory. So it goes to somewhere else, like into RAM probably, okay? And then it just keeps on going over and over throughout this cycle, okay? So these are like fairly low level in terms of computer instructions. So you basically in this case is giving you an example to multiply these numbers, right? So and these are memory locations. You're not actually multiplying 2000 by 2080. It's saying these are the memory locations, whatever the values are in these memory locations, you're going to do a multiply, and then you're going to store it in this memory location. right? So don't try to figure out that you're going to multiply these two to get to this. That's not what this is saying. These are looking in terms of memory locations. Okay. So the memory cycle, right? It's just basically uh, how quickly it's going through this fetch execute cycle. Uh, historically, it was at the megahertz level, but in most recent computers are operating at the gigahertz cycle. So that's how quickly it's churning through all these instructions. So this is kind of like a optimization type of thing. So um, you can look at all of these clock ticks here, and one way to process would be, let's say there's 4 steps, right? Like we said up here, you had to fetch, decode, execute, and store. So that takes it through the whole life cycle, right? So blue, was this orange, red, and green, and that's to process the whole thing. And then once you process that, then you start to process this second instruction, and so on and so forth. So you have a whole bunch of instructions, and you do them one instruction at a time. Okay. Um, Now, some way to optimize this a bit is that each of these are discrete steps. So once you do the first step, you've kind of cleared space that you can actually start on something else. And so instead of waiting for instruction 1 to get all the way done, as soon as instruction 1 is done with one step, um, then, or clock tick, then it will start the process instruction number 2, and so on and so forth. So then after instruction 1 gets done with step 2, then it will move on to step 3, and then this instruction 2 will move on to step 2, and then you can start to load in instruction 3. Right, so in this case, it's showing the first instruction got all the way up to the 4th cycle here, and this one is going to the 3rd, and then this instruction 3 is going to the 2nd one, and you just load it in to process instruction number 4. Okay, so one of the notable difficulties or complexities with this is that this might have some problems if one instruction has a dependency on the results of another instruction. If everything is independent, you're doing a calculation, one doesn't have anything to do with the other, then this all works fine. Okay, but you can imagine if this is maybe waiting for the output of this, you started loading with an old value that is not the right value, right? It can't do anything really until you get the output from this. Okay, and there's various processing to kind of make sure to process this in an efficient way without using incorrect data. So if there's dependencies between one instruction and another, it manages that. The operating system or CPU would manage this. Okay. So this is trying to draw some analogy of what you're doing when you work with a computer, and then how that goes into the CPU, which is basically your working area to do your computations. Um, so it's basically trying to say, okay, you have a refrigerator here, that's where you're storing all the ingredients. Okay, so they'll draw that analogy of the refrigerator to be your secondary storage. This could be your disk drive, could be your memory stick, whatever, right? I think they were talking about a CD before. And then the counter, where you put all of the stuff to process, is considered like your RAM, right? So that's the next level closer to the CPU. Okay, so you take all of this information that was in the refrigerator, put it into your RAM, right? So your hard disk goes to your RAM, so you'll be processing off of that. Okay, then the cutting board, which is sitting on the counter area, that's where you're going to actually do the work, right? So that's where your CPU, in this case, we're talking about the ALU, right here. That's where the work is done, right? So that's the chopping board, okay? And then, so you have the, yeah, so ALU is where the vegetables are getting chopped up, right? Um, and the details about which one to chop up is the control unit, right? So that's like your following your recipe, right? So the recipe on which vegetables to cut, uh, stuff like that. That's here. So control unit, okay? Um, so that's your recipe or your cookbook, okay? So that's this right here, okay? So it's kind of like what I was referring to when I drew that analogy about recipe and the ingredients to cook. And so let's see, well, we have the registers. Um, so basically those are the little working bowls that you have. So while you're chopping up stuff on the cutting board, you might put it into like a little bowl or something, uh, and you can mix things together and whatnot. So that's your registers there, okay? Uh, and then you can write it back out, and then take the salad to like the fridge or the table, okay? So basically how this is just drawing the analogy of what we just talked about up here to like around the kitchen and cooking some stuff. Okay, so this is memory, basically RAM, random access memory. So this is memory that stores the program that's running and the data which the program is operating on, and it's made up of like addresses. So sort of like what we showed you in the multiply here. These are address locations. Okay. Yeah, of course it's finite capacity. Okay. These are different types of external storage. Right. You know all of this. Here's your input and output units, the printer, monitor, keyboard. So this just talks about memory locations. In this case, you're talking about the memory locations being 1 byte each. So something up to 255. So you remember, I think we had some homework questions or quiz or something which talked about the maximum number of characters. I think there was a number of people that kind of got that wrong because they started with 1, right? So they went 1, in this case, 1 to 256. But really it's 0. So you start off with 0 address and that'll go up to 255. So that's how many addresses that you can address, 0 to 255. The actual number is, of course, 256. Okay. I think the whole point here is just talking about, when you run the programs at the level you see, obviously you don't see all these little calculations that are going on here. But basically the CPU is doing all kinds of basic calculations, and it gets built up through these levels of abstraction. So you don't, as a user, you don't see all of those low-level operations. You just see some functions that are built up, which works perfectly fine. Okay, so this is software layers, software stack, some people might call it. Okay, so you start off with the operating system, right? That handles all the basic stuff, right? You would never be sitting there trying to tweak how we access the hard drive. So you would be looking at the operating system through these applications here. Okay, so you work your way through. These are basically building layers upon layers, so that whichever level you're working at, you work at the right level that you need to operate on something. hardly anyone is ever programming at the machine level or working at the machine level. There are some use cases that cause that to happen. For the most part, for most normal people, you wouldn't have to operate at that level. But it's easy when you hear it. There's basically almost like building blocks. You can just connect things together, and just let them do its thing, and you don't have to worry about all these different low-level complexity. So that's what they mean by software layers. Okay. Uh, Another way to look at it is levels of abstraction, right? So that was something that we referred to earlier when we first started the class, okay? Um, and there's some notes here talked about some different things in terms of reuse, consistent behavior, and let's say fixing a bug or whatnot, okay? So I think we've covered all of the different concepts here. Oh, so branching and jump instructions. We didn't cover in here, but I'll just tell you. So a branch or jump instruction could be like, let's say you have your, let's say we come back to the analogy of the recipe, right? So you had your whole recipe, um, and there could be something like, if you're allergic to peanuts, then don't process peanuts, don't mix peanuts in there, right? So you wouldn't go through the parts of the recipe that were to add nuts to the processing because you're allergic to it, right? So if allergic to peanuts, skip, and then you kind of skip down a few steps to whatever the next ingredient is that you have to process. Right, so that's really what this branching and jump logic talks about, right? So what I just gave you an example of is essentially like a jump logic, right? Um, a branch type of thing might be like, if you have a small number, let's say if you have less than 50, do this processing over here. If your number is greater than 50, then you do another set of processing here. So that's what you're talking about when you do a branch for your instructions. Okay, but other than that, I think we hit on all of these points here. But if there's any questions, feel free to let me know. So thank you.